Welcome to this talk. It's entitled, Why Do We Need 5G and IoT? It's non-mathematical and really at the level of a public science lecture. It's extremely important at this time of a COVID-19 pandemic because the role that cellular telephony, IoT, digital technology will play will be pivotal. So I really need to start this lecture in an unusual way. Because we're in the midst of a COVID pandemic, I have to say just a little bit about the COVID 5G conspiracy theories that have been going viral around the world. First of all, 5G does not spread COVID-19. It does not spread it somehow or other through the air. It does not mutate your DNA. Unfortunately, by the 6th of May 2020, 77 base stations, masks as they're called, for cellular radio had been attacked or burnt. And in addition, many engineers had also been attacked who were installing or repairing these masks. And 5G Wi-Fi has absolutely nothing to do with 5G cellular. 5G Wi-Fi refers to the frequency 5 gigahertz. But I suppose if you're the sort of idiot who attacks engineers and base station masks, then you get them all mixed up. So to put 5G and IoT, Internet of Things, into historical context, I really need to look at the origins of cellular communications. So some engineers had amazing vision. You've probably heard of the word Tesla and the company Tesla, but did you know that it came from Nikola Tesla, who was a Serbian engineer? And in 1926, only 4 years after the first BBC wireless radio broadcast, he was predicting that cellular phones, which you could fit in your pocket, would exist. And that was about 73 years before they actually happened. So how did electrical communications all start? Well, we have to go back to the Morse telegraph in 1844. And the Morse telegraph was simply a circuit that allowed current to flow through an electromagnet. And as the telegraph key was pressed down or up, it pulled the electromagnet on the telegraph sounder and gave you the long, short symbols that are very familiar with Morse telegraph. Of course, the Morse telegraph was actually digital, so the first electrical communications was digital and not analog, which is rather strange. Now, in order to get rid of the wires, we need wireless communications. And the mathematical proof for wireless communications came from James Clerk Maxwell. He was a Scottish physicist, mathematician, and he proved in theory that electromagnetic waves could travel through the air without any wires. But he was unable to prove that in practice. The people who proved it in practice were many, and they included Heinrich Hertz, a German physicist. But one of the most important people in proving that wireless communications could take place in practice was Marconi. He was a self-taught Italian engineer who came to Britain, and he experimented and showed that electromagnetic waves could first of all travel over small distances, hundreds of meters, then kilometers. And eventually in 1901, he was able to transmit Morse code 2,000 miles across the Atlantic. An incredible achievement at that time. Now, Marconi needed a way to amplify the signals that he was transmitting and to amplify the very weak signals he was receiving. And he also needed to find a way, instead of transmitting wireless telegraphy like Morse code, how he could transmit voice signals. And for that, we had the beginning of 20th century electronics with a Thermionic Valve. Basically, you have two electrodes, a cathode and an anode. You heat up the cathode and electrons flow towards the anode. And with the Thermionic Valve, you could have amplification. You could produce high-frequency electromagnetic waves on which you could put the voice signal, and also you could switch these valves off or on and store bits of information when computers first appeared, 1940s, 1950s. These led to the development of radio, radar, television, and as I said, computers. Now, the problem with these valves were they heated up, and like old light bulbs, they blew. They were also very, very bulky. So it was miniaturization that gave us the development of modern electronics. So if we look at the valve, say from 1904, that was replaced by the transistor, which used semiconductors like silicon and had exactly the same effect as the valve, but were only about the size of your thumbnail. However, these transistors were discrete until someone had the idea of taking the silicon and etching all the different transistors onto the silicon, as it were, so you had an integrated circuit. In 1971, an Intel 4-bit CPU had 2,300 transistors. If you fast forward to 2019, you could get 30,000 million or 30 billion transistors onto a modern chip. That's a modern chip. The silicon is about the size of your thumbnail. That's 30 billion valves onto something the size of your thumbnail. And it's this miniaturization that gives you the power that you have in your cellular phone, which of course is not a phone, it's a computer in your pocket. So with the development of electronics, we were able to have two-way mobile radio. Here's an example of one that was sold to civilians, because of course we had this inside the forces. But this is not cellular. And also it's extremely bulky, and the batteries won't last very long. But the fundamental problem with two-way radios or broadcast communications was this. You have a transmitter transmitting to a receiver. And the two problems are, imagine you only had 100 frequency channels in the whole of the country. Then you could only have 100 simultaneous users. And the second problem was that as the receiver gets too far away, it loses signal power. So how do we overcome that to get the cellular phone that you all have today, where you can make a call to anybody, anywhere in the world, from anywhere? So the cellular phone concept, I first remember seeing this with the original Star Trek film. And it was Captain Kirk using the communicator, which seemed like science fiction at the time.
Scotty, beat me up.
And the cellular phone concept, when it was developed in real life, it first originated as an idea in the 1940s, but it wasn't until the technology was available in the 1970s that it became commercially realizable. And the idea was very simple. You broke the country up geographically into cells, that's those different colored hexagons. And each cell uses, say for example, each colored cell of the same color uses the same 100 frequencies. I just chose 100 frequencies to make it simple. So as there are 7 different colored cells, you only need 700 frequencies in the whole of the UK. Now there's no interference between differently colored cells because they're using different frequencies. So the green cell and the blue cell, although the users will be close to each other, close to those base stations, they won't interfere. The only interference you'll get is when you're transmitting on the same frequency. So that means to blue cells, or to yellow cells, or to pink cells, etc. So let's see why the blue cells don't interfere. And the reason is clear, is that the blue cells are put geographically far enough apart so that by the time the signals travels from one blue cell to the other blue cell to interfere with someone using the same frequency, all the energy is dissipated. And so you get no interference between same colored cells using the same frequency, and that's due to distance. So that means you can reuse the same frequencies in the blue cells in another blue cell further and further away. And you do that for all the 7 cells. So that means you can reuse the 700 frequency channels across the whole of the UK. And that, in essence, is the cellular phone concept. overcoming the problem that you need lots of frequency channels in order for everybody to be able to make calls at the same time. So as you're making a call from your car, you're connected to a base station, and as you move along, you switch from one frequency to another to different base stations without even noticing it. So how do we get from the very first cell phone up to the current 4G cell phones? Well, I need to start with something that I've called 0G. And 0G was the old landline, and there's a very famous red telephone box. The telephone was invented by Alexander Graham Bell in 1876. Unfortunately, those old red telephone boxes are now only used as toilets. So first generation, that is the first cell phone, came along in 1979. They were analog. They were used only for voice transmission. And the bit in green is really the technology that separates users. It's called frequency division multiple access. So these analog phones, they had no security. People could listen in very simply. They were bulky. You lost the call. But as time went on, they developed and became better. And roughly every 10 years, we get a new generation. So 2G appeared in 1993, and it was digital. It had a data rate of 14.4 kilobits per second because it transmitted both voice and data. And of course, the killer application that made 2G so successful was the SMS text message. I have to say that at the time, the idea that you would take one of the most complicated radio communication systems in the world and use it to transmit short text messages seemed bizarre. But what did I know? Or what did anybody else know who thought it was rubbish? 3G appeared in 2001 with 3.1 megabits per second. I should point out that these bit rates are the bit rates that were in existence when the phones appeared. They increased over that 10-year period. And this was really the beginning of multimedia. You could transmit images, you could connect to the internet, etc. But it wasn't until 4G that you got truly what we call now broadband with an astonishing 100 megabits per second. Compare that to 14.4 kilobits per second, which was only about 16 years previously. So the question is, we've got 4G phones, and they're pretty good. What is the current problem? Well, that's some Gregorian Latin chant. And I'm playing that because this image is St. Peter's Square, Vatican City in Rome, in 2005. And if you look closely, what do you notice? There's only about 2 mobile phones. And if we fast forward to 2013, we can see that everyone is taking pictures, taking videos, and sending these back to their friends. A bit later, and they'll be doing live Facebook broadcasting. So the problem that we have with all those pilgrims and tourists in Rome taking pictures and sending video back to their friends and family, and all the other applications that you have on your cell phone, is that there's an exponential increase in mobile data. So what we've got here is a data forecast for the years 2014 up to 2019, and we're plotting exabytes per month on average for each one of those years. Now, an exabyte is a 1 with an amazing 18 zeros after that 1. And what we mean by this exponential increase is that for any 2 years, for example, for 2018, 2019, the amount of global mobile data traffic will equal to the sum of all the data ever transmitted right back to the very origin of the cell phone. That's exponential increase, and it's completely and utterly unsustainable. Now, If we transmit more and more data, we need more and more bandwidth. And bandwidth is the range of frequencies over which we transmit that data. There's a limited amount of bandwidth available. And as an example, I've considered bandwidth to be the width of a motorway. So if you have a narrow motorway, think of the cars going down that motorway as the bits per second. If you increase the width of the motorway, you can transmit more cars or more bits per second. The problem is that the bandwidth is limited, and as we're going to see later, it's extremely expensive to buy. So I've plotted here, and don't worry if you can't read the writing, the bandwidth allocations from 3 kilohertz up to 300 gigahertz. So a gigahertz is 9 zeros after that 300. And everywhere in there, someone has got an allocation. So it might be terrestrial television, it might be satellite digital audio broadcasting, digital video broadcasting, it could be Zigbee, it could be Bluetooth, very low frequency submarine communication, cellular radio transmissions. The point is that the spectrum that's available is mostly full up. And if you want to purchase some of that, it's expensive. The other thing that we're concerned about is, as the amount of data we're trying to transmit increases, we need to process faster and faster. And we've been able to do that because of something called Moore's Law. And that says the number of transistors that you can put on a chip doubles every 18 months. That's the miniaturization I was talking about before. The problem is now that that increase, which has been solid since the 1960s, is starting to flatten off. And in fact, what's happening now is that we're cutting those circuits on the silicon down to just 25 silicon atoms between the various components. So once you get down to atomic level, you cannot pack in any more transistors. So two things: limited bandwidth, limited processor speed. And that's the problem that we've got, and that's where we are today. And that's leading us on to talk about 3 other issues: Industry 4.0, IoT, and 5G. So 5G as a solution to those problems that I've just enunciated. So what is Industry 4.0? So you're all familiar with the first industrial revolution, really, which was the idea of steam in order to power factories and power trains. We call Industry 2.0 is the idea of electric power and the mass production assembly line. Example of that would be Ford, who really developed that assembly line concept. Industry 3.0 is the advent of computers after World War II, 1950s, 1940s. And here we have Industry 4.0. Now this is really important because this is where IoT, this is where 5G is going to be used, and it's for what's called the smart factory. It's not just robots, because we've had robots for quite a while, but it's this. It's 5G for the fourth industrial revolution of what are called cyber physical systems. And a cyber physical system is where you embed artificial intelligence and machine learning into machines and devices while merging IoT with humans' physical lives. And that's the fundamental difference. It's this idea of cyber physical systems. So what's an example of a cyber physical system? So imagine someone moving a robot in another country remotely controlled via virtual reality. So we have a system here where, if you look at the bottom of the page, the operator is using a virtual reality headset and via a cell phone communicating with a cell tower, eventually reaching the internet via the core network and being transmitted to another country via Wi-Fi access point and controlling that robot. So that's an example of a cyber physical system. So we've explained what Industry 4.0 is and what a cyber physical system is. What is the Internet of Things? So the Internet of Things is internet connectivity in physical devices and objects to 1. Wirelessly sense, 2. Control, and 3. Communicate. And here's some examples. It could be security in your house, it could be in avionics, It could be your washing machine. It could be in your car. Sensors will be everywhere, and they will be wirelessly connected. So the idea of wirelessly sensing, controlling, and communicating could be the security camera at your house, which senses some motion outside. It then controls and locks the front gate and communicates via the internet with, I don't know, the police or yourself. So there are many applications of IoT in smart cities, and as an example, we've given some applications that might see around the world in smart agriculture, smart cities, smart wearables, smart healthcare, a huge growth area, smart water management. And we could expect 75 billion IoT devices by 2025. So finally, what is 5G? So 5G is fifth generation cellular radio. So it's not 5G Wi-Fi, which is 5 gigahertz Wi-Fi. It refers simply to the frequency. And 5G is not just a transition from 4G giving you faster downloads. So it's not just about voice, video, or data. It's also driven by the need to serve IoT. And it's going to be transformative and disruptive. That's the important thing to remember. So let's look at 3 important 5G specifications. It's going to have to deal with enhanced mobile broadband. Now what that is, examples of a large music event or a sports event where you'll have huge amounts of data because everyone's using the phone, or examples where you're using gaming or virtual reality. So this is for high data rates and high capacity. The other example is ultra reliable, low latency connections. Now what do we mean by that? So ultra reliable just means you cannot afford the connection to fail. You cannot afford to have any errors. And examples there are driverless cars, robotic surgery, or drone communications. You must also, of course, have strong security and low latency. So latency refers from the time between transmitting, say, a packet of bits and those packet of bits being received. And we're talking about needing to get down to 1 millisecond in order to have, for example, driverless cars function safely. And the last example is massive machine type communications. So this is where we have a very large number of devices. Each device might only transmit a small number of bits, small number of data. However, you have large numbers of them. So the devices themselves will be low complexity. And examples of those might be smart watches, Fitbits, or all the sensors around your house. So the idea is that 5G will unify the Internet of Things, machine-to-machine, device-to-device communications, and other wireless systems. And I put a question mark there because that's still open to debate. But according to Cisco, we would expect 500 billion wirelessly connected devices by 2030. So what are the new applications that are driving 5G? I've selected here the most important that are agreed by most engineers and most economists that are driving forward 5G. Of course, driverless cars, immersive gaming, production line robotics, robotic surgery, and finally, augmented reality. Now, another important area where 5G will be so different from all the other generations of cellular phones that came before will be machine learning. In summary, machine learning really represents algorithms that allow computers to actually learn from the data. As they get more and more data, they learn by themselves. And a good example of that would be Google's deep learning algorithm, which was used for a diabetic retinopathy. And what it did was we took images of the retina, and those images of the retina were classified by trained physicians. They were then fed into this neural network, and the neural network was trained with these 128,000 classified images, either classified as a healthy or a diseased retina. And slowly, the algorithm learnt to detect what was different between a healthy and a diseased retina, and was able to do that with 91% accuracy. So that, in summary, is going to be one of the major differences between 5G and 1, 2, 3 and 4th generation phones. This integration with machine learning. So we've explained Industry 4.0, IoT and 5G, how they're all connected. Now, how do we actually achieve 5G? What do we actually do to achieve this new 5th generation of cellular radio? So one thing, at the moment when we make a call, we transmit from our phone to the base station up on one frequency and down on another frequency. Now, it might not seem very difficult to transmit up and down on the same frequency, but in fact that's been a huge problem. And it's been solved recently by using the same technology that is used for noise cancelling headphones, strangely enough. So if we now transmit up and down on the same frequency, then we save half the bandwidth because we're not using two different frequencies. And the reason that's so important, as I've said before, is that spectrum is very expensive. For example, in the 4G sale in the States in 2014, 65 megahertz cost $45 billion. So in theory, you would save $22.5 billion by transmitting up and down on the same frequency. Another change that we'll do is we'll have drone-assisted cellular communications, or mobile flat platforms that will allow communication between satellites and cellular users on the ground, that can be used in disaster situations where you've a loss of capacity. You can fly in drones to give you that increased capacity. Likewise, where you have large music events or sports events, those drones can move in effortlessly to give you that increased capacity. We can also move up to higher frequencies, or what are called millimeter wave frequencies. So at the moment we're operating under 6 gigahertz. But if we move up to a higher frequency range where we have some spare capacity, we can transmit at those higher bit rates that we need to. And these are called millimeter wave frequencies. We will also have something called massive MIMO. And MIMO stands for multiple input, multiple output. And what that means is that the base stations will have many antennas. And then with very advanced mathematical signal processing, we can focus very narrow beams on each individual user. So there's no interference from other users, and we increase what's called the signal to noise ratio, and therefore we can transmit those high bit rates without any interference. We will also do something called caching popular content locally. Now what that means is that if you go to the train station and every day you open up your phone and you read the news on a particular newspaper, you have to send that information from a server down to your phone. And if everybody's doing it at the same time, that can overload the server. So why not cache, why not store that popular content locally? And there's a rule called the 90-10 rule, and it says that 10% of objects are accessed 90% of the time. It applies in business. 10% of your customers give you 90% of your profit. So if we cache locally to where the user needs that information, then we can build spatio-temporal models for data caching. That is, we can say at what time and in what place might we most need that particular type of information. Another example of the technology that might allow 5G to be achieved is device-to-device communications. So instead of devices contacting the base station and then going back to some server to get information, you can pass that information through a sort of network of mobile users that are all close together. So that's called D2D, or device-to-device communications. An example might be, say, at a festival where you want to pass information throughout the individuals at the festival rather than having to go back and overload a main server. So we've explained some of the technical methods by which 5G will be achieved. Let's have a quick summary of the 5G technical specs. So the data rate will go up by 1,000 times by area compared to 4G. The latency, that's the delay between transmission and reception of a packet of bits, will be 10 to 30 times faster. The connection density, that is the number of connected devices, so that will include sensors, IoT sensors, cell phones, will go up by a factor of 10. The spectral efficiency, that's how many in that analogy of the motorway, how many cars you can pack onto a fixed bandwidth, that will go up by 3. And the energy efficiency will go up by 100. Now that's very important because many of those sensors will have to sit for maybe 10 or 15 years with a single battery. So you don't want to use that energy all in one go. You need to have energy efficient protocols and algorithms. So finally, mobility, that is, how fast can we travel while still making a call? And that will increase by about 143%. So that's a summary of the 5G technical specifications that we need to achieve. Now let's quickly look at some business aspects of 5G and IoT to put in context all the technical developments. So here we have an example of in 2018 compared to 2024. So in 2018, we'd be transmitting, say, 28 exabytes per month mobile data traffic. And in 2024, we'd be transmitting 131 exabytes. So the size of the donut has increased, but more importantly, if you look at the amount of audio that we're transmitting, which originally, of course, was what the cellular phone was designed for, it's minuscule. Most of the mobile data traffic will be video. Now, with the advent of 5G, it doesn't mean that the legacy networks 2G and 3G and 4G will disappear. They won't. We'll still have a significant legacy component up to 2024. In fact, 5G networks will only carry 35% of all mobile data traffic by 2024. Now, I've kept this slide in to show you how difficult it is to try to predict things. This is from a Barclays 5G survey in April 2019. And I would have talked about the optimistic and pessimistic predictions, both for business revenues and additional jobs. But unfortunately, a lot of things have changed since April 2019. There has been the issue of Brexit, which is not still totally resolved. There was a new government and a new leader. And of course, finally, there was coronavirus. So I'm afraid all those predictions have gone out the window at the moment. And likewise, the predictions for the 10 IoT applications to drive growth through 2020, I've listed some of them here. This is from the Boston Consultancy Group, as I say, prior to coronavirus. Fleet management, connected cars, track and trace, that's very important. Smart meters, remote patient monitoring. I had to add this extra one myself, which is coronavirus. And I decided to look at a few applications that have very quickly come out from academic institutions in dealing with this coronavirus pandemic. So let's just have a quick look at those. This is one that's come out from EPFL, a university in Switzerland, and it's a thermal camera for fever detection and track and trace. So they're suggesting that what you have is, you have a thermal camera that will detect whether you've got a possible fever or not. It will have increased accuracy than normal thermal cameras. And what it'll then do is that as you leave the airport or the restaurant, it can then track you using normal cameras and then trace you, contact you, and perhaps trace your contacts as well. So it's a way of tracking, tracing, and then isolating, but doing it automatically. Another application that comes from EPFL in Switzerland is an analysis of cough audio. So the World Health Organization says that 68% of people who have the virus present with a particular dry cough. So remember I told you about artificial intelligence and machine learning. What you do is you train an algorithm to recognize the particular characteristics of the cough. So then you can cough into your phone and you'll get a message saying that perhaps you should see a doctor because you might have COVID-19. So there are dozens and dozens of applications, new applications or repurposed old applications that are now appearing to deal with this COVID-19 pandemic. And finally, here's an example in the lockdown in Singapore where a robot dog made by the very famous company Boston Dynamics was running around the park warning people to social distance. I think that this wasn't so much a practical application as an advertising event for Boston Dynamics. So I want to see if I can pull everything together here with an IoT case study. And I'm going to choose as an example a company in Donegal that has IoT startups called INCRYPTON, and it's to do with monitoring the cold chain for food and medicines shipped across the world. And the company is run by Dr. David Gray. So as an example, imagine I want to send a vaccine from Derry to Chongqing in China. So I'd have to ship that by lorry down to Dublin. I would take a flight from Dublin to Beijing, and then say another flight or a train to Chongqing. So all along the way I'm going to be using planes, trains, lorries, etc. And I have to be sure that those important vaccines have been kept within a certain approved temperature range. So how can we be sure that they have? That's the important question. Okay, so what's the design philosophy for the solution, the IoT solution to this particular problem? So the first thing is it has to be simple to use, because all along the route there may be people who may not be the most technically aware who need to make a simple check to see if the vaccine is still okay. That is, has it been residing within inside an approved temperature range? Secondly, there must be no way of tampering with the information, i.e. saying that the vaccine has been inside the approved temperature range when in fact it has not. And finally, the device that you're going to design has to be cheap. And my colleague Dr. Gray decided that it would have to be $1 or less. So those were the three important design philosophies for his particular business. So how did he satisfy the three design principles? Well, he came up with this $1 microchipped blockchain QR badge. Now, what does each one mean? Well, $1 is obvious. It costs $1. Microchipped, there's a small microchip in that. Blockchain is really a distributed ledger system that's often used with cryptocurrencies, but gives you complete and utter security. And it's on a QR badge. So how does that work? So there's a simple test. This is the simplicity with your finger. You move your finger across the green bit in the middle, in which there's a light sensitive device on the chip. And if it goes green, it means that the temperature sensor is telling you that the temperature has been fine all along the way. And if it goes red, it means it hasn't. So that's the simplicity side. And you can get a detailed temperature history via a light transmission from that sensor to your smartphone. So instead of using electromagnetic waves, Dr. Gray decided to use modulated light. It was actually simpler. And what he had to do there was he had to alter the actual camera mechanism itself to act as a receiver for that light transmission. So $1, it's cheap. Blockchain, it's secured. A simple test by moving your finger over the green part to get a yes or no, that's the simplicity. So in order to get a detailed temperature history, then you use the light from the chip to your smartphone to transmit the bits of data. And this is what you would get. So here we have an example of where, for a very short time, the temperature has strayed into the non-allowable red zone, too hot, and also into the non-allowable blue zone, too cold. But it's been over a very short time, so we say that that is still a good product, a good vaccine that you can use. But here we have a situation where it's strayed too long into the red zone, a short time into the blue zone, but that is now considered to be a bad product. So let me finish with one question. Should we trust technology predictions? I don't mean those predictions before COVID, because that was a once-in-a-lifetime thing. But in general, technology predictions. Some have been accurate, one or two have been completely wrong. And here's a really extreme example. This is Dr. Joseph Fromkin, a PhD in economics from the University of Chicago, and he was an IBM economist. That means he was the economist for IBM, one of the biggest manufacturers of mainframe computers. So he was there when it was all starting, and he should have known what was going on. But he said this. In 1965, he said, computer automation will eventually bring about a 20-hour work week, and we will live a life of leisure. Now, I don't know about you, but I'm not living a life of leisure on the beach much of the time. I wish I was. So let's finish with some conclusions. So 5G, unlike 1G to 4G, is a disruptive and transformative cellular technology. It will also enable IoT devices in many applications where you need, for example, low latency, where it's a mission critical application, where you need energy harvesting to conserve battery power, etc. And it's driven by the needs of autonomous or self-driving vehicles, robotic surgery, industrial robotics, IoT, augmented virtual reality, immersive gaming, smart cities, factories, healthcare, wearables, and of course, machine learning. And finally, along with IoT and cyber physical systems, it will enable what has been termed Industry 4.0.